All right, everybody, come on in, sit down. Still a couple of seats up front. I promise not to throw too many things. Oh. All right. So this is the point at which I say, hopefully you're here for CS 162. If you're not, you should jump up and scream, I'm in the wrong classroom, and go out and go somewhere else perhaps. But welcome. My name is John Kubitowicz. Most people can't pronounce my last name, so they call me Professor Kubi, and you're welcome to do that as well. And I'll introduce myself a little bit later, and the TAs as well. But welcome to CX 162. This is a huge classroom. I'm assuming there are a number of you that are on the wait list. How many people are on the wait list still? A few of you? Okay. We'll talk a little bit more about that. But let's start and dive in here just to get moving. One of the things that I think is so exciting about right now is we have this big artifact that a lot of people in the rest of the world are not aware of. You're very aware of the internet. Everybody can kind of look very carefully at this. There are many slices like this that you can see. If you actually look carefully down here, you'll see that this is from ancient history. This is 1999. But if we took one from today, what you would find is there's actually so many nodes you couldn't even possibly, you get this sort of solid ball. And what's so exciting about this is not just that it provides new ways for everybody to communicate and tie civilizations together. It also is starting to talk about tying everything else together as well. Okay, and we're going to talk a bit about the Internet of Things as we go on, which is a new buzz phrase being used by lots of companies. I don't know, I've even started seeing commercials about the Internet of Things, and that's when you knew something has truly arrived, I guess, when it shows up during Big Bang Theory or whatever it is you like to watch. But it's kind of interesting to see graphs like this. What you see in the far left is 1969, probably a year that most of you have never were not around at that time. And what you see is a little tiny thing here called the ARPANET. And what was interesting about the ARPANET was the addressing of the ARPANET could not allow more than 256 nodes on the network. Okay, you guys may even have 256 nodes in your home network today. Okay, but this was the ARPANET. And what's kind of interesting is during this period from 69 to 90, there was a whole lot that went on in terms of communication, but in fact, the rest of the world that's not academics really didn't know about it until 1990s when HTTP got announced, and then all of a sudden we had this explosion of users, and at this point we had a small number of users. At this point, we've got Facebook, and this exponential growth in users, and last count we have probably about 3 billion people that are all interacting over the internet. So this is pretty exciting artifact. Now, of course, this is not a class on networking, but this sets the context for this class. Okay, and I actually think that this is probably one of the most exciting times to be working in operating systems, because as an operating systems person, you got to figure out how to manage all of these users and devices. Okay? And, operating systems really are at the heart of it. And they're the things that are controlling the complexity. Now, of course, there's some interesting aspects of hardware, which I'll mention a little bit too, which has really enabled all of this. But it's kind of interesting when you can have graphs that are meaningful to people about how Android App Store overtook the Apple App Store at a certain number of apps, and we're talking 700,000 or 1 million apps here or there. And this means something to my dad. Okay, that's kind of cool, right? And I won't go into the religious wars over, whether you're an iPhone person or an Android person. But what is interesting is all of these operating systems have kind of key building blocks in them. They've got scheduling, concurrency, address spaces, protection, isolation, security. Boy, we'll have to say something about that. Networking, of course, all sorts of distributed systems issues. There's persistent storage. How many people here store data in the cloud? How many of you know what that means? Wow, okay. How many people think they know what it means but probably don't? Yeah, those are the honest ones. The cloud is this funny nebulous thing, which I'm going to have a few things to say about later in the term as well. But this notion of persistent storage is important. I'd like to take pictures and make sure that they're around in 100 years or 1,000 years. Assuming people are going to care about my pictures in 1,000 years. Of course they are, right? But let's start with something pretty simple here. So if you were to say, what's in a search query? Everybody here has done a search, right? Even if you are an Apple user. An Android user. So what happens when you go to search something and find something on the net? Well, the first thing that actually happens is, and this is very complicated, right? The first thing is your search site or website has to actually talk to a set of DNS servers. Those DNS servers communicate with one another and transform your human readable name into an IP address. And then from that IP address, which comes back, then it gets to route through the rest of the internet. Now this picture is a little funny because the DNS servers are actually on the internet, but I thought I would separate this for a moment. And, that request goes through, and then it goes to some big data center somewhere, and Google, Yahoo, Amazon, you name it, they're all like this. The request comes in, and there's actually a load balancer which takes your supposedly unique IP address that you got, and it actually chooses which of a whole bunch of different servers are actually going to satisfy that. And then the search is completed over a whole cluster of machines in the cloud, whatever that means. And then your result comes back, and then of course you've got to add ads in there because, what's a good search without an ad for whatever weird sort of thing that you might want to be getting, and then it comes back with your response. Now, if you look at all of these pieces in here, there are operating systems underneath all of them. So obviously there's the Apple iOS in this picture. There are probably Linux or, probably Linux running on the DNS servers. The internet routers have some unique real-time operating systems on them. The data center itself, the load balancers probably also have a real-time operating system on them. The search indexes are probably back to Linux again these days. The ad servers, probably Linux again, but certainly coupled with huge storage, lots of storage, lots of disk drives, SSDs, and so on. And that's all managed by operating systems. The result comes back, and voila, you get your search. So you did something pretty simple, you thought, but there was a whole bunch of components involved. And what's interesting about that, as far as I'm concerned, is that somehow it works. Has anybody ever thought about the fact that that actually works? Okay, kind of surprising, right? I've seen pieces of this go together over the years, and the fact that it actually does work is astounding to me. Okay, and I allow you to be astounded as well. You should be, because it's pretty complicated. And you'll be able to understand all the pieces. But the fact that it actually gives you a result is pretty interesting. Okay? So why should you take 162? Well, some of you are actually going to end up designing and building operating systems. Is there anybody in here who feels like they want to be designing operating systems for their life? Okay? A few of you. That's good. That's a kind of a fun place to be because operating systems are branching out into not just, Linux or iOS. They're actually getting into pretty interesting sort of realms these days. Many of you are actually going to create complex systems that use the operating systems. And maybe you're going to build software, some of you will build hardware. And these design patterns that we're going to come up with actually show up at all levels. So what's kind of interesting is, technically speaking, as I'll say a little bit later, I'm actually a computer architect. Although I've done a lot of work in operating systems as well over the years. And the ideas in computer architecture show up in operating systems. And the ideas in operating systems show up in computer architecture. So these concepts are very transportable. And then all of you are going to build applications. Okay, for no other reason than you have to pass the class here, so you get to build some applications. But I'm going to assume that you're going to do more applications as time goes on. Okay? So this is probably a good reason to take 162. So today, what I want to do is give you a little bit of an introduction to where we're going this term. I'm going to tell you a little bit about what an operating system is and maybe what it's not. We'll talk a little bit about some examples of operating systems design. I'm hopefully going to help you understand why it's so exciting to be designing operating systems and what makes every sort of new operating system a little different from the previous ones. And somewhere along the way, I'll actually tell you something about the class, since it is the first day and you want to know kind of what you're getting yourselves into. But okay, are we all ready for this? Does this sound good? Okay. So what is an operating system? Well, this is kind of interesting because you ask 5 different people who actually design operating systems what the operating system is, and they'll all give you slightly different answers. Okay, so some possible good answers are a convenient abstraction of complex hardware devices. So you got hardware that's complicated. The OS abstracts it in a useful way, so you've got applications on top. Okay, that's a pretty good one. Some might say it's a way of providing protected access to shared resources. So this hardware has some resources like disk drives and network cards and so on that are going to be shared, and the operating system gives you protected access to that. We're going to say a lot about what that protected access really means in the next month or whatever, but among other things, you can imagine that if you store your files in some part of a disk and somebody else is using the same piece of hardware, you'd like for them not to be able to just get your files. Right? So there is some level of protection there that's desirable. So clearly there's security and authentication involved, and there's also communication among logical entities. So among other things, for instance, these applications need to communicate with each other and so on. So that might give you a little idea what an operating system does, but probably not enough. It's an operator of form, right? So this is actually before my time, believe it or not. But, there was a time where you made a phone call and there was somebody that actually plugged a wire in, okay? And there were computer operators at one time that actually had to coordinate a lot of resources. Today, operating systems, modern operating systems tend to do a lot of the same coordination that you had humans doing at one point in time. Okay? So what I want to do as a very gentle introduction here is say a little bit about some OS basics, and then over the next couple lectures we're going to dive into a few more of those basics. And one of the reasons we're going to dive in sort of at a user view is it's going to be your first couple of homeworks in this class are actually going to learn the system level programmer's view of an operating system so that when we actually dive in, you'll have an idea what you're talking about. Okay, rather than diving in to the depths of operating systems right away, we're going to get you a little bit of a user's view of them. And so in a typical situation that requires an operating system, you've got software and hardware. Okay, that's not too surprising. But inside that hardware, you probably have a processor and memory at minimum, and then you have some devices like storage devices. These might be disk drives, they might be flash storage devices. You have some networks, you have some displays and other inputs. And the real trick is how to give a nice, clean abstraction layer, basically for the software to get access to this hardware. Okay? And so that is typically called OS hardware virtualization. It's a way, basically, of taking this hardware, which is going to vary a lot, and giving you a virtualization of it that's sort of common across a lot of hardware, and as a result, it's easy to program. If you imagine what would happen if you were a programmer that had to adapt every piece of software that you wrote to every possible piece of hardware that it was going to run on, you'd go crazy, right? So this abstraction layer actually gives us the ability to write the software once and run it in many places. Okay? Now, part of this virtualization layer, we can kind of look in the hardware. We talk about the instruction set architecture, and that gives us the ability to put the hardware virtualization layer together, and on top of that, we're going to design things like processes, address spaces, files, windowing systems, sockets, threads, etc. These are some of the concepts that we're going to want to get access to right away in your first few hardware assignments that are provided by the OS virtualization layer that make it possible to design software. So basically, this virtualization layer, or the operating system in many cases, are going to provide these guys, and then the software, the writer, is going to write on top of them. And that's going to be where we're going in the first few weeks. Now, this is one of my favorite, very old slides from David Patterson. Anybody taken a class with Patterson? Okay, he's always very fun. But this particular view of the hardware-software interface is really, he used to say, this is Microsoft dancing on Intel. Okay, and so this is basically Intel holding up the solid interface so that the Microsoft software guys can dance on top of it. Now, of course, what does that really mean? It means that somehow this firm instruction set never changes, and then Microsoft can take advantage of that to write good software. Okay, and why are interfaces designed in a particular way? Well, if you took 152, you'd find out that there's a lot of stuff in computer hardware architecture that's really historic. Okay, that, the Intel processor is that way just because it ended up that way. Okay, and there's a lot of classes that we have, like 152 and 160 and 169 and so on, that all look at various interfaces and things like, should responsibilities be pushed across boundaries and so on. But it's really, the more important thing to get out of this sort of discussion is it's about coming up with a nice clean layer that other people can use while you're working underneath. Okay? And that's kind of, in this class, the hardware virtualization layer. I will, by the way, relate an interesting story. I can't resist since I'm an architect, but there was a time in the 90s when there was a bug in the floating point unit. Did anybody ever hear this story? Okay, there was a bug in the Intel floating point unit such that if you use the divide instruction, a small number of bits were wrong, and that would affect a very rare number of applications that needed extreme precision in their division. Okay, so what was Intel's reaction to finding this? They set out and told their customers, well, you have to convince us that you really need that accurate a division, and if you manage to do that, then we'll give you a new chip. Okay, now what happened was they pissed off a lot of customers. Okay, how dare they ask me to prove to them that I need their hardware to work? And that was actually a disaster for Intel, and they eventually ended up giving them out to everybody who asked. Okay, but the interface is so incredibly important. It actually made it to the New York Times, by the way. You can imagine, when was the last time a bug in a piece of Microsoft software made it to the New York Times? Ask yourself that question. So back to our little story. So we've got this question of how we turn programs into processes, which is going to also be something we learn about next time, pretty much. And the idea here really is, what is the difference between a program and a process? Well, a program is the thing you write. A process is an instance of the program that's running. Okay, so you imagine you write your program once and you run it 5 times. There can be 5 processes, which are 5 instances of that program. Okay, and so what that really means is the software that you've written gets loaded into memory, and now you've got a set of registers in the processor that are now devoted to it, and as a result, that program becomes an executing entity or a process. Okay? And of course, there's an operating system which also needs to run, and so one of the things that's kind of interesting is this notion of context switch, which we'll talk about, which is this processor is busy devoting its registers to the memory, but a timer interrupt shows up, and now as a result, we sort of clone the registers that matter for that process and put them aside, and now the processor is busy running the operating system instead of the program, and what it can do is pick some other program to run and switch back, and now we had one program running or one process running, and we switch over to another process that's running. Okay? And that is how you get the illusion of more than one thing running at a time, even when you only have one processor going. There's a timer interrupt. Operating system takes the current process, switches it out, puts a new one in, runs it, and it switches fast enough that you don't notice the difference. Okay, that's called a context switch. Are there any questions on that? Okay, so, and of course, another interesting thing is if we're going to have lots of processes, because there are many different programs all loaded and many different instances of programs loaded, and so now the question is sort of who decides which instance of a program or which process actually gets to use the processor. That's called scheduling. Okay, and that's kind of interesting because the scheduler, there are many varieties of schedulers. Some of them are real-time. We got to make sure that when you press the brakes on your car, that car stops. How many people think that's probably a good plan? Okay, all right, well, I'll keep that for you if you don't think that's a good plan, but it's a pretty good plan. You can imagine other scheduling decisions like I want to make sure among all the processes that are running, there's fairness. Everybody gets a fair share of the processor. Okay? Any of you, we've had some terminal servers in the departments over the years where you log in and you're sharing a machine with lots of people. Am I really dating myself here, or has anybody experienced that? And what happens when too many people are logged in? Very slow. Okay, the reason is, of course, the operating system is busy switching between all of those people trying to be fair, but the net result is you see such a little bit of the processor, you get annoyed and go get your coffee and then come back hopefully at midnight or something when it's less used, right? So that's scheduling. The other thing that's kind of interesting is protection, and protection is very important here because if this green process tries to stomp on the red process or tries to read private data from the red process, that's a problem. And the protection mechanisms basically prevent that kind of cross-flow of information. Once again, this is an important aspect of the operating system. Okay. Now, this protection boundary we typically think of as kind of dividing all the pieces of hardware in the operating system from the user-level processes that are running. And these are all words I'm throwing out here. You'll know what they mean soon if you don't now. So finally, of course, a big thing that the operating system does is I/O. And what I/O really means is I/O means providing a virtual abstraction of the devices to the processes that are running. And, so typically we have a storage abstraction, which is called a file system, right? We typically have a networking abstraction like sockets, which we'll tell you a little bit about what sockets are. And that abstraction is got to go through the protection boundary because, once again, you can have different people's files stored on a given disk and want to make sure that different processes only get access to the files they're supposed to. Okay? And under the covers is a whole bunch of hardware. I'm going to show you a picture a little bit more about this later, but lots of stuff that as a user you don't have to worry about. Okay? There's controllers and buses, and different interfaces that the disks are plugged into, and all of that stuff is managed by the operating system in a way that you, as a user, when you're writing software, don't have to worry about. Right? The simplest thing to think about is you store your files, let's say pictures. You store pictures from a camera on a little USB stick. How many people own a USB stick? Okay. And then you plug it into your laptop and it gets stored on the disk drive. Those two types of storage are completely transparent as far as your file browser is concerned, because you go to the file browser, you go to the file or the disk drive that is the disk drive, and you pull pictures off of it and copy them over to the USB stick and vice versa, and you don't have to care that there's a physical USB stick under there. You could just as well be copying between two USB sticks or two disks. It's the same thing. Okay? And that's all what the operating system has to manage. And it is interesting, I don't know what the absolute latest statistics are, but there have been many statistics about why operating systems crash. And by the way, what is the number one thing that causes operating systems to crash? To the tune of more than 43 to 50% of crashes are caused by this. Anybody want to hazard a guess? Yeah. Drivers? Yes. Device drivers. Why? This is the great question, right? So why do device drivers tend to crash operating systems a lot? Anybody want to give me some reasons? Yeah. Sure, okay, so yeah, you can plug them in or take them out without really warning the operating system so it doesn't know what's going on. What else? Yeah.
You're lower level, so if you make a mistake, like abstraction, I guess.
That's right. So they're in the kernel, they're at very low level, so if the device driver makes a mistake, we got problems. What else? Yeah, the back. Yeah, same idea, right? I've got access to all the memory, I can screw it up. Anything else? Yeah. Yeah, so third party, there we go. I was definitely looking for third party. So the problem is device drivers are written from somebody who's not the operating system writer. Okay? And as a result, you have no idea the quality of the device driver. Okay? And how many of you, and I'm going to raise my hand here, have a new device and you say, oh, you got to download a device driver, and you say yes. And this is not signed correctly by an authority that anybody knows about. Do you still want to download it? Yes. Right? And the net effect is you probably just loaded a virus onto your machine and didn't know it, right? Now, of course, we're all betting on the fact that we didn't do that. But, yeah, device drivers are dangerous, and they're also very unstable. So, interesting. Okay. Now, of course, the last little thing I want to mention here is this notion of loading. So, of course, software doesn't really sit up in space like this, except on slides, right? The software is really on the disk somewhere. And as a result, the way you execute a process is you actually have to go through the process of loading the program into memory and then starting its execution. Okay, oops, lost. Dum-da-dum. All right, I've done that my once for the term here now, so we're good. Won't happen again. Okay, so yeah, so basically without this loading process, the files would stick on disk somewhere, they never execute. So there's clearly part of the operating system needs to be responsible for loading off the disk, linking in dynamic libraries, doing all sorts of stuff. Okay. We good? So that's a very quick whirlwind tour of some of the interesting topics. And of course, we see up here threads, address spaces, processes, files, windows, sockets. These are all topics in a typical OS class. And we're going to basically revisit them a number of times, first from the system programmer viewpoint and give you some homeworks that let you basically dive in and write some programs that use these ideas. And then we're going to dive in deeper and actually implement some things like threads and address spaces. Okay, so you're going to start by using them and then go on and become the programmer. Okay, so what really makes operating systems exciting? And one of the things has to be Moore's Law. And so, by the way, every class, it's mandated, every EECS class has to have Moore's Law slide in it somewhere. So I just want you to know, this is my due diligence. This, by the way, is actually Gordon Moore. And the story that is quite interesting, and by the way, what's Moore's Law for those 3 people in the audience that don't know what it is basically this idea that on a log linear scale, where linear is the years and log is the number of transistors, you've got a straight line, which really means the number of transistors grows exponentially over time. And so that's why we've got such interesting pieces of computer hardware, because we're adding more and more and more transistors every year and allowing ourselves to do more things at lower power, okay? And that's why I have, on my belt, a device here that's got way more power than filled rooms, okay? 40 years ago. And of course, it actually runs an operating system that's way more complicated than the one running on those computers 40 years ago. Okay, and that's all really due to Moore's Law. The thing that you may not get in your classes, if you've seen this before, is this diagram. I love this. This is a sketch of his transparency, which, by the way, is a piece of plastic that you used to put on a device like this, and you draw on, and it would project on the wall without going through a VGA projector. I realize that's way back then. But anyway, so what's interesting is this is an actual picture of what he drew, and he was asked at a conference, "You've just designed the 4004 processor. Can you predict how many components are going to be in the future generations of chips?" And what he did was, like any good scientist, he plotted a couple of points on a log linear scale, drew a line, and said, "This." Now, of course, he was right. But it was pretty impressive that the original Moore's Law was literally, he put a couple of points down at a conference and made a prediction. So anyway, so the bottom line here is that because the number of components keeps increasing dramatically, every generation is more complicated and more functional. And of course, who controls functionality and complexity? The operating system. Okay? Now, the other thing that I like, David Culler had this slide and has used it many times. This is like a corollary to Moore's Law, which I think is very interesting, which is if you plot the number of people per computer on a log linear scale, where the year is the linear part and the number of people per computer is on this vertical axis, you actually see another straight line, which is really meaning that the number of computer or CPUs that you yourself have is growing exponentially over time. Okay? And I bet that everyone in this room has 50 to 100 CPUs working for them all the time. They just don't know it. Okay, think about it a little bit. You got a little Bluetooth, maybe that's passé these days, but you got a car with 50 to 100 CPUs in it. You've got your laptops, you've got your cell phones. You add it up, it goes pretty quickly. And so this is again a sign of complexity because now we've got so many more components that you have to manage. And a second interesting thing, this is another mandatory slide in classes. How many people have actually seen this slide before? Wow, okay, I got a whole new audience here. So this is from a version of Hennessy and Patterson's book that was published around 2006. And what it shows here is this is not Moore's law. This is what was often called Joy's law, which is the increase in performance on a log linear scale was also exponential in the sweet spot here until about 2002. That was, in that sweet spot, you could be lazy as a programmer. You had a program that was too slow, don't worry about it. Just wait for a year or two, run it on a new piece of hardware, it'll work fine. Okay? And around 2002, something happened. There was this sudden change that made it hard for industry to stay on that curve. So it used to be, by the way, that this particular 52% per year represents about doubling in performance every year and a half. And what happened here was somewhere around 2002, this curve fell way off. And there are many reasons. If this was an architecture class, we'd talk about them, but things like power density got too high, capacitance was too, per transistor got to be in the way, and so on and so forth. Lots of reasons. Instruction level parallelism got harder and harder to find. The net effect of all of that was that suddenly you couldn't wait. You couldn't just take a bad piece of software and wait a little while and it would get faster. You had to actually re-architect it. Do anybody know what was the response of Intel and a bunch of companies around here? What happened? Multi-core, right? So now, how many people have a multi-core phone? Yeah, most of you, right? That is pretty crazy. A decade ago, I would have raised my hand and people would have looked at me a little strange. You know, they do that anyway, but they would have about my statement there. And the reason is that multi-core is a relatively recent thing. Okay, and suddenly we had to have parallelism, which made the complexity harder and gave more work for the operating system. Okay, and so many core chips have really kind of taken the front stage, and what I think is a good harbinger of things like that is, for instance, in Intel actually had a couple of experimental chips. Here, this one was back in 2007, was actually an 80-core multi-core chip. And they had, and that was just a lot of simple cores. And then there was one more functional that had a smaller number of cores, but a lot more interesting network. And what this really showed was, okay, industry can make multi-core chips, and they're going to do it, and they're going to grow in interesting ways. And what do you do with a chip like this? Well, first of all, I guess many core people debate, maybe it's 64, 128 cores, whatever. But the way you program this thing is you use 2 of the CPUs for video and audio. You have 1 for the word processor, 1 for your browser, and 76 of them are devoted to virus checking. Okay. Now, of course, that seems a bit of a waste. And it was kind of funny when these big chips first came out. Nobody really knew what to do with them, and they're getting a little better. But the bottom line is you could imagine processes each getting a core. That's a boring way to use them, but it's a thought. Right? You got a bunch of things running, you put 1 per core. Okay. So basically we have to have parallelism everywhere. Okay. So another challenge that I think is kind of interesting, which is one of the reasons that this curve fell off, was really power density. And basically if we as computer designers had continued along the path of Moore's law and increased performance, what you would have found is that by 2008, basically the power density inside a chip that's in your cell phone and your belt would have been about the heat coming off of a rocket nozzle. You could imagine that would be rapidly rather uncomfortable. I guess you would have to switch which hip it was on every now and then. So that was another reason why people went for parallelism. They just couldn't afford to make faster processors. Okay. So because we're doing Moore's Law-like graphs, let's do a couple more. Storage capacity, this one really matters to operating systems people. What's interesting here is, again, the amount of storage on a log linear scale is also a line. What's the current size of a disk drive that you can buy for a desktop, let's say? Anybody know? 10 megabytes. 100 megabytes. Terabyte. Okay. 4 terabytes. Boring. 6 terabytes. Yeah. 8 terabytes soon. 10 terabytes announced. That's a lot of storage. Okay? That's a lot of storage. I'm very happy to say I just bought a new TiVo that has 6 terabytes on it. I'm happy. That's a lot of Big Bang Theory or other things. Okay. So the other thing, of course, that's growing is I like Big Bang Theory. I like other things too. But so the other thing is that network capacity has been growing pretty rapidly. This is interesting because this lets you tie a lot of things together, okay, and make interesting, complicated artifacts, which is going to lead us to the Internet of Things soon, which all have lots of little operating systems tied together in a big global operating system. So the idea of an operating system of operating systems is actually not completely crazy. Okay? Now going back to the Internet for a moment, the Internet scale, they actually measure this thing, and this is a little bit old data. This is from January 2013, but there's actually 0.96 billion hosts on the Internet that are measurable, and it was actually going up in July and so on. And why is say 96 billion, 0.96 billion an interesting number? What is it close to? 1 billion. Okay, that's dumb. The number I'm looking for here is 4 billion. Why is 4 billion an interesting number? Yes? Yeah. So if you were to look at IPv4, and we'll talk a little bit about that for those of you that aren't quite familiar with it, IPv4, which is kind of the prime Internet addressing mode for most of the Internet these days, really only has 4 billion unique addresses. And so we're basically coming up to a number of unique hosts in the world that are very close, way within an order of magnitude of the total number of addresses. Kind of interesting. And of course, also close to 2.5 billion users. People track all this, and you can see it by region. It's kind of interesting to actually look at how a lot of the third world countries have a lot more users per population than you might expect. It's quite rapid growth. So the Internet is basically reaching everywhere. Okay? And not only PCs are in the Internet, of course. Obviously, smartphone shipments have exceeded the desktop shipments for several years now. So in 2011, for instance, 487 million smartphones were sold and 414 PCs. So PCs are blasé. Some would say that means hurry up and sell your Intel stock, although I think Intel has been moving into the mobile market. But it's kind of an interesting change, okay, to mobility. Okay. 4 billion phones in the world. And they're all going to smartphones, so that's a really big market everybody's going after. And of course, this is an old slide that keeps getting reused because the ideas are kind of interesting, but this is sort of the societal scale information systems where everything from the little tiny smart devices all the way up through the global cloud and everywhere in between are all part of one huge parallel system. So you could say, well, I've got a cell phone and it's not part of a big parallel system. You'd be fooling yourself because think of all of the apps you've got that are tying into your cell phone provider, all of the searching you do on the Internet, everything else. Basically, the only way to go off the grid is to disappear somewhere in the heart of, Montana. Anybody here from Montana? Probably a few of you. Have you disappeared yet? No. So very hard not to be connected. And this is like a major thing. Everything's connected to everything else. And of course, what's driving that? The operating systems. Okay, have I made that point pretty clear? Okay. This is a good topic. You guys picked a good class. So let me say a little bit about who I am. Professor John Kubatowicz, I said most people call me Professor Kubi, and that's kind of interesting. Patterson, when I first came here to Berkeley, tried to say, okay, now that you have a grown-up job, which I guess meant not graduate student, but okay, he says, you should go by John. Okay, you got to be a grown-up. It never happened. Okay, everybody called me Kubi, so you can too. So I have a background in hardware design. I was on the Alewife project at MIT, where I helped design the communication and memory management unit. Was a modified SPARC processor, and built one of the first parallel machines that actually did shared memory and message passing together in the same piece of hardware. Okay, that's a picture of my chip, which has an embarrassingly small number of transistors today, so I won't tell you, but it was a few years ago. So I have background in operating systems, lots of backgrounds. I worked for Project Athena, which was one of the very first organizations that actually built distributed computing, where students could sit down and their files might be on a remote computer rather than on the local disk. We built Kerberos. We built all sorts of things that hadn't been heard of before. Kerberos is an authentication service that actually is deep in the heart of NTFS and a few other Microsoft projects these days. So that was an exciting project. I was an OS developer, developed device drivers and network file systems, worked on clustered high availability systems for a company called Clam Associates, which was clustered storage, basically. And right now, I'm actually the OS lead researcher for Tessellation OS, which is an operating system that we're developing in the Swarm Lab. I'll tell you a little bit about that as the term goes on. I did a lot of work with peer-to-peer when I first got here. I was the lead on the OceanStor project, which was one of the first real peer-to-peer storage systems, which now you call it cloud computing, whatever the cloud is, right? But we were kind of interested in storing your data for thousands of years by continuously repairing the data and transferring it around. And today, there was our logo, which was a scuba diving monkey, which makes perfect sense if you think about it, right? And don't think too hard. So today, I'm actually working on a new project called the Global Data Plane for the Internet of Things, which is also looking at raising the abstraction from TCP/IP to information that's transferred, stored, archived over the long term. And so we'll talk about that. But it's a better abstraction for designing some of these devices. And then also, I actually have a hobby. I sort of work on quantum computing every now and then, and it's totally unrelated to this class whatsoever. Sometimes I do an extra lecture at the end of class that has nothing to do with the topic or whatever topics people want. And if you're interested, by the way, we could do that. And sometimes people ask me to talk a little on quantum computing, so I might get persuaded. But if you want to talk about other things, that will work as well. So that's me. As you can see looking around, this is a very large class. And right now we have a very large number of people that are in the class and a very large waiting list. But the reason we have such a large, because we have such a large class, we also have a very large number of TAs. Okay, and for everybody who's here, can you basically stand up and turn around and wave at everybody? Stand up, TAs, are you guys here? Okay, good, yeah. So we got, some of them are still, our head TA is still in India. He's traveling back. But we have quite the team. This is a really amazing team this term, and I think it'll make the term go really smoothly. I see that my formatting's a little funny here, so you guys can obviously figure out that the pictures go down a little bit here. But there are 12 sections. And anybody not assigned to a section, that should have gone through Telebears, everything should be fine? Okay. Anybody here not have a section? Lots of you? Okay, good. Well, I guess we'll deal with that when the time comes. So by the way, if you go to the website, which I'll mention in a moment, everything about which sections are where and what TAs have what hours are all up. So we actually have infrastructure, the website, which is your end-all and be-all of information related to the class, is, as you see up there, it's cs162.eecs.berkeley.edu. And if it isn't on the website, it doesn't matter. No, if it isn't on the website, you can ask the TAs about it, but that's probably a good place to say, do I know when the due dates for something actually are? Because we're going to try to keep that website actually up to date. Whereas anything you hear from me could be hearsay, including the fact that operating systems are interesting. Maybe that's just hearsay. But if the website says it, you should take the class. We're also using Piazza. And I believe that's the right link, although right now the website has the old link, so we're going to fix that. But it is 2015. And yes, we are hopefully webcasting. I think the answer is yes. And if we aren't today, it will be starting next time, but for sure. So we'll post a link to where the webcasts are. And I don't know if they're going to show up on YouTube like they have in the past, or if there's something different. But any questions about infrastructure? Okay. So I like to use the website as a great place to make sure everything's posted. In fact, I think one thing we're going to change about the website is even have a little bit of a notes thing, although the website and Piazza together is your sort of full set of information. The textbook we're actually using is a little different than past terms, except for last term. We're using the second edition, Anderson and Dahlin, Operating Systems, Principles, and Practices. It's a pretty good book. It's soft-bound, so it's not $500 like your other textbooks are. I actually just went on Amazon and got this pretty reasonably, but I think probably Ned doesn't have it because it hasn't been taught enough. Is there still Neds? Does he still sell used books, or is that a thing of the past? Anyway, what was that? He's gone? Too bad. He was good. It's like, you want a textbook? Here. But I strongly recommend you get this book. It's very good. It's well done. It sort of beats out the previous one pretty in its clarity of thought, and so I like it a lot. We'll be following along pretty closely with several of the topics that are in here, so it's a good book to have. And it also is a good textbook for keeping on your shelf for reference in the future, so I think that's good. Try to get the second edition. I made a mistake. I figured I'd be clever and I'd hurry up and order, and I couldn't get it on Amazon the day I was going because they were sold out, so I went to Barnes & Noble, and I ended up accidentally getting the beta first edition by not looking at the cover. So this one's got a lovely picture on the front, snow and mountains and trees. The other one's got kind of a boring, total white cover, so look for the snow and mountains and trees, and probably the fact that it's a second edition on there might be a good sign too. The other thing is this previous book, Operating Systems Concepts, you can probably get from other people that have taken 162 in past terms, and you can also get it in the library, but we're going to have a few readings from this on things that aren't covered in this textbook. And then we'll have also online supplements on the website, and this includes some appendices and sample problems and other supplemental reading. And one of the things that I like to do in the OS classes, and I haven't put them all up yet, but I like to occasionally have actual research paper reading, so you can see things that we're talking about from the standpoint of the researchers. So there are a few topics like that that are kind of nice. Research papers tend to be short. They're a 10 to 12 page thing, so they're not awfully long. So I won't be overwhelming you with too much reading. But any questions on infrastructure or readings or textbooks? Yeah?
How much are we at a loss if we got the other version of the book?
Did you get the one with the white cover?
Yeah, that's what Telebear is
It's, it's not bad. I've been reading the white-covered one because I didn't have the one with the beautiful picture of, by the way, the snow and the mountains and the trees. Did I mention that? You're probably okay. But if you have a friend that's got the other one, you might want to occasionally check. I haven't compared them head-to-head yet, but the newer one certainly has some typos fixed, and there's some concepts that are a little cleaner in the second one. It's clear the one I got, it was a beta. It even says beta copy on the inside. I don't know if yours does, but you know that that's probably got some bugs. White is black and black is white, and 4 equals 3, except on Sunday. Those are the kind of things that end up in a beta book. But any other questions? Okay. So syllabus is OS concepts. Actually, we're going to start with how to navigate as a systems programmer. And so things like processes and I/O, networks and VMs, and so on. We're going to talk about concurrency, so thread scheduling, locks, deadlocks, scalability, fairness, things like that. I'm hoping that when you come out of this class, you'll know how to properly synchronize something if you're asked to do it. You might actually understand what deadlocks are like and so on, and that's a very useful thing in this day and age. You'll also know how to design thread packages to some extent. We're going to talk about address spaces, virtual memory, address translation, protection, sharing. We're going to talk about file systems. We're going to talk about distributed systems of various sorts like RPC and NFS and distributed hash tables and consistency and scalability and so on. So there'll be some interesting things there. We're certainly going to talk about reliability and security since that's kind of the number one key topic. Especially if you use your credit card at stores like Target. You got to be careful. But we're going to talk a little bit about where you can go wrong on some of these things in the course. And then we'll also try to talk a little bit about cloud infrastructure. I just put that down as a sort of a buzz phrase, but that's going to include things like the Internet of Things, which I do think is pretty exciting going on right now. Okay, so you're also going to learn by doing. And so in this class, we're adopting something new that I actually did in the Advanced OS class that I taught a few years ago, was really we're going to have a combination of individual and group work. And the reason for that is that you want to make sure that you as an individual clearly get a handle on how to do things like use C, which is the language we're going to use here. And notice I say recall C, although for some of you it may be a little bit of learning C. We're going to learn how to use the tools. You're going to learn how to use Git, okay, because Git is one of our key sort of mechanisms that we have in this class. The second homework is going to let you learn how to do some shell programming, so you'll actually know how to do that. By lab number 2, which is the third lab, you're actually going to be able to build a web server, so you're going to get to use some honest-to-goodness good tools. And then another important thing is we have group projects, of course. And the group projects, anybody here never had a class with a group project? A few of you? Okay, so the group project adds an important dynamic because those of you that are, go out into industry will have to deal with groups unless you're going to do a really small startup. Okay, if you do a really small startup in your basement, actually, you probably need a Keurig, a pile of coffee, a computer. Maybe that you can avoid a group. But anywhere else, you're going to have groups, okay? And so this is an important aspect of doing this kind of systems programming, and you're going to get a chance to do that. This term, we only have 3 projects. 2 of them are using something called PNTOS, which is a C, an operating system written in C that you're going to get a chance to actually do some thread programming and some address space programming to produce processes. And then the last thing is going to be a key value store, which as of right now is still in Java, although we're going to see what happens with that. Okay? So we are not using Nachos this term. Okay? Just like they didn't use Nachos last term. We're trying something new. So to get started is homework 0 handed out today. Actually, it's handed out yesterday. I'm just kidding a little bit, but you got to start now. And basically what it's going to do is sort of go ahead, you're going to walk through homework 0 on the website. It's going to get your CS162 account. It'll get a GitHub account. It's going to go through some registration. It's going to get your VM environment, etc. You're going to get used to all of the tools. You're going to learn how to submit to the autograder. You're going to basically get to sit down and do a bunch of stuff just so you're ready to do other stuff. Okay? So homework 0 is really about learning how the class is going to work so that when you get to do the interesting things, you don't have to worry about that other stuff. And that's why you have to do it starting today, because you got to get going on it. For some of you, this is going to be a little challenging because you've never used these tools. Every one of you will be able to easily use these tools. These are really good tools. You just have to learn how to do it. Okay? It's do it the first time and you'll be great. This is individual. So the homeworks are individual. The group projects are in a group. Okay. And also, sections start this week. So if you don't have an officially assigned section, I guess go to the section that fits your timing. For now, the section postings are up on the website. But the reason the sections are starting off right off the bat is, once again, getting to learn how to use the tools you'll need for this class so that you're not struggling with things that are sort of how to use Git or how to program in C or how to do some of these things. Okay, now, how many of you consider yourself C programmers? You could sit down and you could write a huge 5 million line C program after breakfast with a good cup of coffee. Okay, nobody. We got one. Good. He'll help you all. No. So, the thing I want you to realize is we don't have a lot of classes yet that program in C, but this is very important. It's the language of operating systems. And so what I suggest is you right away get going with C, get comfortable with it. We're going to post on the website pointers to some books on C if you want to walk through a little tutorial. Okay. What did we miss? Pointers? Pointers for pointers on pointers. Oh, that's very good. Yes. Yeah, one of the fun things about C is pointers, of course. That's pretty good. I'll have to remember that. Pointers for pointers on pointers. Thank you. Now, I don't know how everybody know what the O'Reilly books are, the ones with the animals on the front? They're great, right? They're fun little books. They have a topic. There are good O'Reilly books on Git. There are good O'Reilly books on C. There are good O'Reilly books on Make. The nice thing about being on a Berkeley subnet, or at least within the department, anywhere on campus, you actually have access through the digital library to the O'Reilly books. And so there are lots of O'Reilly books, and you can read them electronically without actually having to purchase them. It's like going to the library, but with your laptop. Okay, and so I actually, I've asked the TAs, I don't know if we've done it quite yet, to actually post links to some key O'Reilly books that are available online for everybody. So that may help you a little bit and get going too. Okay? But I guarantee it, if you spend time in the first week or 2 weeks actually really getting your infrastructure going, the rest of the term is going to be smooth. Okay? And this is, I can't overstress this. It seems like, starting right off the bat. But it's really stuff that doesn't require huge amounts of thinking, but it does require you to have done it once or twice, and then the rest of the term will be smooth. All right, wait list. So we have a huge wait list, and the class size is not set necessarily by me. It's set by the department, and it depends on lots of things that I have no control over. So the other thing is, this class is an example of the type of lab class that if you're in a group and you decide things are really rough halfway through the term and you drop out, then your group is in trouble. And so this is one of these, 162 has been designated an early drop class, which means there's an early drop deadline here. So you need to decide if you're going to go forward with this class. And I believe January 30th is Friday, is the day for dropping. And this is really to make the rest of the class smooth, because in the past we've had groups that sort of disappeared halfway through because a key member disappeared. So anyway, if you're not serious about taking the class, I guess you get forced to make a decision point at January 30th, but keep that in mind. Now, as far as the wait list, this is going to be a great class, by the way, of course. TAs are wonderful. The lecture is not too bad. But I think it'll be much smoother if we don't have people dropping in the middle. The other thing I will point out is, again, the wait list is not under my control, so that basically we're taking people in a department accepted order. We let a bunch of people off the wait list. I think we've got right now like 325 or something that are actually in the class, and I think that's kind of our limit. The number I'm pulling out of the air. It's not an exact number, but it's somewhere around there. And again, that's the department. Okay. Questions on the wait list? If I had my druthers, I'd let everybody in. It's just the class would get unwieldy if it got too big. We may try to do bigger ones in the future, but I think we've got a pretty big limit right now. Any questions? No. Okay. So what are these group projects? So group projects pretty much simulates an industrial environment, as I mentioned, unless, again, you're that one person in your basement. Project teams, this term, are going to have 4 members. Okay. In the past 162, we said 4 or 5. 5 is too many. 3 is too few. So we're going to do 4. If you really, 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 really need to have a 3-person team, you need to justify it to your TA, and we need to talk about it. But try to do 4-people teams, okay? That will be an optimal configuration. And basically, in the real world, you're going to have group interactions, and so group interactions almost never go smoothly the first time. Anybody ever experienced an unsmooth group? Don't raise your hand. So I'm actually going to say a little bit in a few lectures about sort of ways of managing groups and so on to help a little bit with that. But one of the things you get with the group interaction is you learn how to communicate with your colleagues, and problems with communication are completely natural. If you have a group that runs 100% smoothly, you're in the minority. That's pretty cool, but you're in the minority. And you need to figure out kind of how to get the communication and how to document between your members and so on. So the other thing that is going to be an interesting aspect of this is you should think of your TAs almost in the managerial role, your team's working and they're your manager. And if you think of it that way, one of the things that's kind of interesting about that is the design document requirement is really about a high-level description for a manager that's not in the trenches with you. It's very easy when you're confronted with a design document, and we'll put up some sample one to see what we want, but it's very easy to say, document every little detail of everything you're thinking you're going to do, and you end up with a 500-page document that nobody wants to read. Okay, and that's not what we're going to want. We're going to want you to be documenting your code very well, but also producing a clean design spec, and we'll try to give you a better flavor for what that's about. Okay? Any questions? Good. What about grading? So 2 midterms and a final, 40%. The exact proportions haven't quite been figured out yet. 40% are projects, 15% of the homework, 5% participation, which really means it's a good idea to know your TAs well because they know how you participate. I will hopefully get to know many of you. I'm not likely to end up knowing all of you by the end of the term as much as I would aspire to that. But hopefully we can get somebody who knows you well. Project grading is going to be a well-defined rubric, which we'll put up a little bit later. Every submission will be submitted with git push, so that actually triggers the autograder. And one of the things we're going to try this term, and I'll say more about this as we get closer to the project, is actually pushing your projects to your own repositories several times before you do the final master push. Okay, because your TAs, who are your managers, are going to want to get some insight into what you're doing as you're designing things. Okay, and don't worry about that for now. There'll be more details. Okay, questions on grading? Okay, midterms are likely to be in the same time slot as the class, and some combination of this and another to be announced place, I think. I haven't quite figured out exactly how we're going to deal with that. So of course, I have to say a little bit about personal integrity code. So there is an honor code, as you're all aware. As a member of the UC Berkeley community, I act with honesty, integrity, and respect for others. What that really means is things that are kind of that are okay in this is explaining a concept to somebody in another group, discussing algorithms or testing strategies with other groups, helping to debug someone else's code, maybe in another group is getting okay, is probably okay. Searching online for generic algorithms like hash tables, fine. Okay, so these are probably okay. Things that are definitely not okay, sharing code and test cases with other groups. Copying or reading another group's code. Copying or reading online code or test cases from prior years. Okay, these are not okay. And we actually have some software tools that we use to check on that. So just try to be on the up and up and do your own work and your own group's work, and this will work out fine. Okay? Good. So let me say a little bit about my typical lecture format. Today's not a typical lecture, but basically it is kind of funny. Years ago, and this is becoming almost long enough ago to become lost in urban legend, but we actually had somebody who knew something about how people learn that came and attended some of our lectures, and they were listening to people give lectures, and what they found is the first thing that happened was people came into the classroom, the faculty member came in and said, okay, before we get started, I want you to know that this Friday we actually have homework 3 that's due, and group projects are due this, and they got through a whole bunch of administrivia right at the beginning of class. And what this person said was, well, wait a minute, people learn, their attention is highest at the beginning of the class, so starting off with boring administrivia is a really bad idea, okay? And what it really amounted to was that people learned the administrivia of the class really, really well, but when it came to the actual topic matter, they kind of waned and sort of lost their attention. And so what we're going to do is the following, because this is a 1.5-hour class, which is pretty long. We're going to do the following. So people come in and their attention is really high. Okay? And so I'm going to talk some interesting things, whatever it is, something about the class, and probably even have a little bit of a summary of the previous class at the beginning to make sure you're on the same page. And what's going to happen is, of course, after about 20 minutes, your attention's going to start to wane. And at that point, we'll take a bit of a break of some sort. Okay? Now, oftentimes, that break involves administrivia. It might involve talking about what's due. It might involve something interesting in the news, whatever. The idea is try to get your attention back up. And, of course, whatever it is going to be restful enough that you're going to come back up. And so we're going to talk for another 25 minutes, and you guys are really going to be doing well. And at that point, we will probably actually break so everybody can, run outside briefly for a few minutes and get a drink of water or something, and that'll probably help a little bit. It won't be as high as before, and then we'll talk some more. And the key thing to watch for is when I'm ready to finish, I'm going to say something like an in conclusion. Okay, and what happens with the in conclusion? Well, obviously, ta-da. Okay, now you gotta go with it, right? So wait until you hear what I'm concluding, so you can figure out what the best things you learned from today or should go with before you pack up and run out the door. Okay, and then of course you guys will be off having fun. All right, so. Anyway, so that's my typical lecture format. I'm going to try to break it up into kind of 3 pieces like that. So we'll see how well that works. Sometimes it works, sometimes it doesn't. But it's basically, a quick minute review, 20-minute lecture, 5-minute administrative matters, and so on and so forth. Okay? So we'll try for that. Today's a little different because it's kind of a mixed lecture in sort of a weird form. Today, I do want to point out, however, that interactivity is extraordinarily important. So yes, I've been sitting here talking at you all lecture, but I'm going to want to have lots of questions. We're going to do some, interaction. There'll be some interesting debates, perhaps, going on. And so watch for that, because interaction makes the class much more interesting. Okay? Having somebody lecture at you for an hour and a half is very hard. Although it is useful that there's like a coffee house right over here, so I suppose afterwards you're exhausted, you drag your way over to the coffee house. That might be one way to get past a long lecture, but we won't do that to you. So let me just finish up here. We got a few minutes still. But what is an operating system for sure? What's kind of interesting is this book, the Anderson and Dahlin book, basically say the operating system is three different things. A referee, which is managing, sharing resources, protection, and isolation. It's an illusionist, which is providing a clean, easy-to-use abstraction of the actual resources so that the programmers don't have to worry about the funny details. And it's the glue. These are the common services like file systems, like programming libraries, windowing systems, networking, all of those things that you really need to glue together the pieces of your application to make it work. And the operating system really does all three of these things. And I like this characterization because we can talk in detail about whether a particular item of interest is a referee item, an illusionist item, or a glue item. And, obviously security, real-time behavior, all of that stuff kind of fits in the referee behavior. Some of the libraries that you use fit in the illusionist behavior. Some of the glue can be interesting networking services like cloud storage and so on. So we'll talk about these as time goes on. But the real challenge in all of this is, and I've alluded to this throughout the lecture, is complexity. Okay, applications consist of a whole bunch of software modules that run on a bunch of devices that implement different hardware abstractions and architectures and run different applications at the same time and fail in weird ways and can be under a variety of denial of service or other attacks. And the real question is, in this mess, how do we get anything useful out of it? And once again, remember that sort of query that I started the class with. To do a web query, it's amazing that works. Okay, I want you guys to do it. This is your homework, other than homework 0, which you're supposed to have started yesterday. I'm kidding. But you should go out and do a Google search and think about how amazing it is that worked. Okay, that's your be amazed tonight. Actually do the search and think about it. So really, it's not feasible to test all the possible failure scenarios. It just isn't. It's just not possible. So how do things work at all? Well, they're correct by design. You got to start thinking about, how do I design something so that when it fails or if it fails, it's a mode that's likely to be handled properly, even if I didn't foresee it somehow. And that's pretty hard to do when you think about it. But there'll be some things we talk about a little bit. And so, for instance, here's a modern processor. Okay, I don't know how often you guys have gotten to see things like this, but this is a Sandy Bridge, so this is a couple of years old, but it's got 4 cores on it. It's got a huge level 3 cache. It's got a graphics processor, and then it's got a systems agent that handles a bunch of I/O, and it's actually got a ring bus on it that communicates between the processors. And this is one chip. That's one chip. Okay? And, you look at the Sandy Bridge I/O configuration. So if you have a desktop, you've got basically that one chip. And then you've got basically something that used to be called a South Bridge. And basically this actually communicates with the chip and gives you all of your interesting I/O. And plus it's the chip itself typically has memory, graphics, and so on connected directly to it. But down here you see things BIOS, okay, you see networking, you see serial ATA for disk drives, PCI Express, and so on. All of this stuff is the domain of the operating system because you, as a programmer, don't want to think about it. Now, you as an operating system designer may find this really cool. I do. But at some level, it'd be nice to get away from that and not think about it, right? And that's the complexity at the local level that the operating system is handling. Now, this is an old slide, but this is an example of a bunch of computer architecture topics, and you see everything here from things down at the pipelining and hazards and reordering and speculation and vectors, up through caching, up through DRAM, through SSDs and disks and cloud storage and networking and all of these things. It's pretty complicated, and somebody, namely the operating system, has got to manage that complexity and hide it from everybody except for the OS programmers. And I love this particular slide because this is very old now, but it kind of gives the point, right? If you look at the NASA Space Shuttle in millions of lines of code, that's over here, okay? And then you look at Windows Vista at 50 million lines of code, and you can kind of see the problem. Just in sheer lines of code, you can imagine how the heck does this actually work? Okay, and I like this Mars Pathfinder. You should look up Pathfinder afterwards. This is a fun rover that was one of the most successful early projects on Mars ever. This is a little Martian, by the way. And the Pathfinder had very limited hardware. Okay, it had a 20 megahertz processor. It had 128 megabytes of DRAM. It had a real-time operating system called VxWorks. It had cameras, scientific equipment, batteries, solar panels, locomotion equipment, lots of independent processes working together. By the way, I think this sounds like something I could buy at Fry's these days. Everybody see the quad rotors they sell down there? You can't hit the reset button. The thing's on Mars. Did I mention that? Right? So it's on Mars. It crashes. What do you do? Okay? You have to make sure that you can always reboot it. Okay? It's got to always receive commands on Earth even when it crashes. Okay? Individual programs must not interfere with each other. So suppose the Martian Universal Translator module is buggy. It better not crash the antenna positioning system that makes sure that you can always reboot the system. Okay? All that the software, any software can crash occasionally, so you have to have automatic restart, you have to get diagnostics back to Earth, periodic checkpoints, and so on. And certain functions are clearly time critical, like the need to stop before hitting something. That's pretty time critical, etc. And there's a couple of interesting things to note about this. So first of all, there's a lot of similarity with the Internet of Things because there's a lot of little devices that people are looking at these days that are in places you can't reboot. They have very limited computing power. They have very limited memory, and they're trying to do real-time stuff. And you've got to somehow make sure that you can get at them. Okay, that's one thing. The second, and we'll talk about this when we get into synchronization, one of the things that was kind of interesting is this particular device had a priority inversion problem that would actually cause it to get stuck in rebooting all the time. And they were actually able to download enough diagnostics from Mars to debug it and send the right updated patches and actually fix it, okay, remotely. Right? So there's a lot of interesting lessons for there. But this is a good example of handling complexity and somehow handling it remotely. So how do we tame it? So every piece of computer hardware is different. So we have different CPUs, memory, disk, devices, etc. And the questions are sort of, does a programmer need to write a single program that performs everything? Do they have to be altered for every different piece of hardware? Does the faulty program crash everything? You can ask a bunch of these questions, and we will as the term goes on. And the answer really is that we want to provide standard interfaces. I started to say this earlier, but basically what we're saying is that there is a standardized machine interface, and the operating system is handling that complexity and providing a nice clean API up to the users. And that clean API is doing all sorts of things, like making up for deficiencies in the hardware, like dealing with hardware crashes, like dealing with all sorts of interesting limitations by presenting APIs up to the user that look easier to use. Okay, good example is the infinite file API. Right? So disk drives are finite, but maybe you have an infinite file API by what? Extending into the cloud. Maybe you could do that, right? There's a lot of interesting options there for virtualization. You'll have a lot of chance to run into virtual machines. Anybody here actually use virtual machines? Okay, if you haven't, you will. But there's at least two types of virtual machines. One is what we call a process virtual machine, which is what an operating system provides to support the execution of things, and a system virtual machine, which basically gives you the ability to execute an entire operating system in a container. Okay, and so here's an example of process VMs, which is going to be our next topic. Every process actually thinks it has all of the memory and all of the CPU. Every process thinks it owns all the devices. Different devices seem to all have the same high-level interface, and devices, so that what does that mean? That means that USB key that I mentioned and the disk drive look identical to the higher layers. Okay? And basically that's the process VM. The other thing we get out of this is fault isolation, so that if one process crashes, it doesn't crash others. And we get protection and portability, and so those of you that have used Java, which I think is probably everybody in here, are familiar with some of the protection features. The system virtual machine looks like this, where essentially we have a virtual machine layer that allows us to run several different operating systems in the same machine. So this FreeBSD, this Windows NT, this Windows XP, each of these operating systems think they're running on their own machine, but you're giving them the illusion that they're not, and that's a system virtual machine. Okay, you're going to encounter both of these. All right. So what is an operating system really? Let's close up a little bit. Most likely you could talk about pieces like memory management, like I/O management, CPU scheduling, communications, multitasking, or file systems. Sure, why not? Multimedia support. Sure. User interfaces. The browser. Is the browser part of the operating system? How many people think a browser is part of the operating system? That was an interesting argument that was before your time. We'll talk about that another time. Is this only interesting to academics? It's hard to say. But what's an actual operating system's definition? There's basically no universally accepted one. One person might say it's everything a vendor ships when you order the operating system is the operating system. Okay. The other option is the one program running all the time in the computer is the kernel. Okay, so everything is either a systems program or an applications program on top of the kernel. This is a pretty clean one for the operating system, is the kernel, and we'll probably use that a lot this term. But so anyway, I'm going to finish up for now. I'm going to say in conclusion, we'll talk about processes next time, but operating systems provide a virtual machine abstraction to handle hardware. They coordinate resources and protect users from each other. They simplify application development by providing standard services. And they provide an array of fault containment, fault tolerance, and fault recovery so that when hardware fails, you don't have to know about it. And CS162 is going to combine all sorts of interesting topics from other areas to give you a flavor for operating systems. So with that, I'm going to say don't forget homework 0. Do homework 0. And don't forget to do a Google search after you leave here and be amazed. Okay, those are your 2 pieces of homework. Go to sections tomorrow or Friday.